Το Institute for Advanced Study στο Princeton των Ηνωμένων Πολιτειών της Αμερικής με τίτλο The Meaning of Spacetime, Black Holes, Wormholes and Quantum Entanglement. Τον ομιλητή θα προλογίσει ο καθηγητής του Τμήματος Φυσικής του Πανεπιστημίου Αθηνών, κύριος Κωνσταντίνος Φέτσος. Στο τέλος της διάλεξης θα ακολουθήσουν ερωτήσεις στα αγγλικά. Good evening, ladies and gentlemen. We welcome you to tonight's lecture by Professor Juan Maldacena from the Institute for Advanced Study in Princeton, United States of America, entitled The Meaning of Space-Time, Black Holes, Wormholes, and Quantum Entanglement. The speaker will be introduced by Professor Konstantinos Fetsos of the Department of Physics at the University of Athens. At the end of the lecture, you can raise your questions to Professor Maldacena. Thank you.
Good evening, everybody. The idea is that I give a very short, not a lecture, but a brief introduction on the general subjects that Juan Maldacena has worked. The introduction will be in Greek because the talk is also for the general audience. And after this, Juan, of course, will take the podium and give the real lecture. So, είναι μεγάλη χαρά να παρουσιάσω το σημερινό μας ομιλητή, Juan Maldacena, ο οποίος είναι ένας από τους πιο επιδραστικούς θεωρητικούς φυσικούς της εποχής μας. Το έργο του Maldacena επικεντρώνεται σε μερικά από τα βαθύτερα ερωτήματα της επιστήμης. Ποια είναι η φύση του χωροχρόνου, είναι ένα από αυτά. Πώς μπορούμε να συμφιλιώσουμε τη βαρύτητα με την κβαντική μηχανική. Υπάρχει ένα ενιαίο θεωρητικό πλαίσιο που να συνδέει τις διαφορετικές δυνάμεις και δομές που παρατηρούμε στη φύση. Αυτά είναι από τα σημαντικότερα ερωτήματα που μπορεί κανείς να ρωτήσει στη θεμελιακή φυσική. Η πιο εμβληματική συμβολή του Juan Maldacena προτάθηκε το 1997 και είναι γνωστή ως αντιστοιχεία EDS-CFT. Η ονομασία ακούγεται κάπως τεχνική, αλλά η βασική ιδέα είναι ταυτόχρονα απλή και βαθιά. Δηλαδή, ότι μια θεωρία βαρύτητας σε ένα καμπύλο χωροχρόνο μπορεί να είναι ισοδύναμη με μια κβαντική θεωρία χωρίς βαρύτητα, ορισμένη στο σύνορο αυτού του χωροχρόνου. Η ιδέα αυτή περιγράφεται συχνά και με τον όρο ολογραφία, όπως ένα ολόγραμμα κωδικοποιεί μια τρισδιάστατη επιφάνεια, τρισδιάστατη εικόνα σε μια διδιάστατη επιφάνεια, έτσι και εδώ η φυσική μέσα σε έναν όγκο χώρου μπορεί να περιγραφεί πλήρως από μια θεωρία στο σύνορο αυτού του χώρου. Γιατί είναι αυτό τόσο σημαντικό? Περιγραμματικά υπάρχουν οι εξής λόγοι. Πρώτον, μας προσφέρει ισχυρά νέα μαθηματικά εργαλεία για τη μελέτη συστημάτων που μέχρι πρότινος ήταν σχεδόν απρόσιτα. Αυτό επιτυχάνεται γιατί σε πολλούς τομείς της φυσικής, ιδιαίτερα όταν οι αλληλεπιδράσεις είναι ισχυρές, οι παραδοσιακές μέθοδοι που γνωρίζαμε αποτυγχάνουν. Η αντιστοιχεία EDS-CFT επιτρέπει στους φυσικούς να μετατρέπουν πολύπλοκα κβαντικά ερωτήματα σε απλούστερα ερωτήματα στο πλαίσιο της κλασικής βαρύτητας. Στην αντίθετη δε κατεύθυνση, επιτρέπει τη μελέτη και κατανόηση φαινομένων κβαντικής βαρύτητας, όπως το παράδοξο του Χόκκιν, για τη διατήρηση ημί της πληροφορίας κατά την δημιουργία και εξαήλωση των μελανών οπών. Είναι εντυπωσιακό ότι η ειδικότητα έχει βρει εφαρμογές και έχει προσφέρει σημαντικές γνώσεις πέραν του αρχικού πλαισίου της. Πρωτίστως φυσικά στη σωματιδιακή φυσική, στη συμπεριφορά των κουόρ και των κλουονίων. Σε ορισμένες επίσης εξωτικές καταστάσεις της ύλης που μελετώνται στη φυσική της συμπυκνωμένης ύλης. Αποτελεί ένα εντυπωσιακό παράδειγμα του πώς μια βαθιά θεωρητική ιδέα μπορεί να συνδέσει πολλούς διαφορετικούς τομείς της φυσικής, η οποία πρέπει να γνωρίζουμε ότι είναι ενιαία. Ένα ακόμα βασικό αντικείμενο του έργου του Maldacena είναι η μελέτη των μελανών οπών. Οι μελανές οπές δεν είναι μόνο συναρπαστικά αστροφυσικά αντικείμενα, αλλά και κρίσιμα πεδία δοκιμής για τη θεμελιώδη φυσική, καθώς συνδυάζουν με ακραίο τρόπο τη γεωμετρία του χωροχρόνου με κβαντικά φαινόμενα. Όπως ήδη αναφέρθηκε, μπορούν να περιγραφούν ως κβαντικά συστήματα που διατηρούν την πληροφορία. Το έργο του Juan Maldacena υπήρξε καθοριστικό στο να δείξει ότι αυτή η εικόνα είναι συνεπής με τη βαρυτική περιγραφή, ενισχύοντας την άποψη ότι το παράδοξο της πληροφορίας επιλύεται χωρίς παραβίαση της κβαντικής μηχανικής. Πέραν αυτών, σημαντική είναι η συνεισφορά του Μαλντασένα στην κοσμολογία, ιδιαίτερα στην κατανόηση του πρώιμου σύμπαντος. Το έργο του έχει βοηθήσει στη διατύπωση θεωρητικών προβλέψεων για τις μικροσκοπικές διακυμάνσεις που παρατηρούνται στο κοσμικό μικροκυματικό υπόβαθρο, διακυμάνσεις τελικά που οδήγησαν στη δημιουργία γαλαξιών, άστρων και στη μεγάλη κλίμακα δομής του σύμπαντος. Τέλος, τα τελευταία χρόνια, η έρευνά του έχει συμβάλει στη γεφύρωση της κβαντικής φυσικής με τη θεωρία της πληροφορίας. Μια από τις πιο συναρπαστικές εξελίξεις είναι η συνειδητοποίηση ότι η κβαντική διαπλοκή μπορεί να σχετίζεται άμεσα με τη δομή του ίδιου του χωροχρόνου. Είναι άραγε η γεωμετρία του χωροχρόνου θεμελιακή έννοια ή είναι αναδυόμενη έννοια από δομές κβαντικών συσχετήσεων? Η κατεύθυνση αυτή είναι και το επίκεντρο της σημερινής ομιλίας του. Συνοψίζοντας, αυτό που καθιστά το έργο του Μαλντασένα πραγματικά αξιοσημείωτο δεν είναι μόνο τα αποτελέσματά του, αλλά και οι πρωτοποριακοί τρόποι σκέψης που εισήγαγε, αποκαλύπτοντας βαθιές και απροσδόκητες συνδέσεις μεταξύ βαρύτητας, κβαντικής θεωρίας πεδίου και πληροφορίας, έχει αναδιαμορφώσει την πορεία της σύγχρονης θεωρητικής φυσικής. Οι ιδέες του επηρεάζουν ευρύ φάσμα πεδίων και εμπνέουν ερευνητές σε όλο τον κόσμο. Για όλους αυτούς τους λόγους, είναι μεγάλη τιμή μου να καλωσορίσω τον Juan Maldacena στο Πανεπιστήμιό μας. It's really a pleasure to welcome Juan Maldacena to our university to give this talk. Let's give to him a word welcome.
Thank you. It's a pleasure to be here. I have only one objective for this talk, which is that you understand more than I understood of this introduction. Okay. So let's start with a quote by Galileo, who said that the book of nature is written in the language of mathematics and geometry. So let's explore what this meant. So let's talk a bit about geometry. You know, you probably all studied in school the Euclidean geometry, the points, lines, and circles, and the relations between them. It's about these very basic concepts, and we use it to describe images. It arose from the technological necessities of the time, sort of charging taxis, measuring the sizes of fields, and so on. And the ancient Greeks, so not far from here probably, formalized and abstracted the rules for geometries, and they boiled them down to a series of axioms, and from these axioms you could derive the rest of geometry. Now, there were about 5 axioms, and just to give you a flavor, I'm going to quote one of them. So one of the axioms says that given 2 distinct points, there is a unique line that passes through them. So this is something that looks obvious, and this is one of the starting points of Euclidean geometry. Now, this idea of taking geometric concepts and abstracting them, formalizing them, and deriving then relationships has continued to this day. And we can now imagine curved geometries, higher dimensional geometries, and so on. Now, geometry is a very basic notion. It's about very basic relationships. And we can find it in unexpected places. For example, even in children's games. So I'm going to show you an example just to see how we can find geometry in a children's game. I don't know if you know this game. It's called Spot It. It's a game where you play 2 cards, and the first one to find the image in common. So these 2 cards have one image in common. Please find it. So the first one to find the 2 images in common wins, okay? So here you can find that image in common. That's the image they have in common. And so given any 2 cards, there is always a unique image in common. So in this particular case, that's the image in common. Now, what does this have to do with geometry? Now, imagine you are trying to design this game of cards, right? you have to choose a set of images, distribute them in the cards, and make sure that each card has only one image in common and not more, or no less. Now, this should remind you a little bit of that axiom of geometries, right? So we want to find the distribution of cards and images such that given two cards, there is a unique image in common. This is similar to that axiom of geometry that says that given 2 points, there is a unique line in common. In fact, this distribution of cards and images, we can think of them as points in some geometry, and we can think of the images as, we can think of the cards as points and the images as lines. In some geometry, it's not the Euclidean geometry of the plane, it's a geometry called finite geometry that has a finite set of points. It has this axiom in common with Euclidean geometry, but some of the other axioms are different. So this is an example of how those geometric notions are found in some everyday things. Okay. Now, even for more perhaps current topic of discussion, there is a higher dimensional geometry behind the language models of like ChatGPT. For example, one of the first steps in analyzing text is to represent words as images, as images, as points in a, let's say, 12,000 dimensional space. And that's one of the first steps that they use to deal with language. So we can say, paraphrasing Galileo, that geometry is the language of language. Okay. Now, the contribution of another famous Greek is to realize that the geometry of the Earth is not flat, but is curved. And of course, he did this by this famous experiment of looking at the shadows of a vertical stick. And so one conclusion of this is that Euclidean geometry is actually wrong for measuring fields, right? Because fields are not on the surface of a flat Earth, but they're surfaces of a curved Earth. So if you have a large enough field, the size of a continent, then the angles do not sum up to 180 degrees, though that would be true for a small enough field. So this is a first example of going between a flat geometry and a curved geometry. So now let's go back to physics. So we talked enough about geometry. And let's first recall an important principle from the 20th century, which is the principle of special relativity, which says that observers moving with constant relative velocity observe the same laws of physics. Actually, this first statement goes back to Galileo, the principle of relativity. The new aspect that Einstein brought in is the idea that the speed of light is the maximal speed of propagation of signals, and that's another law of physics. And if you assume that that's the same for all observers, then you get the principle of special relativity. Now, this in particular says that if you have two observers, one stationary and the other one traveling, so the top one here is the observer that is moving at constant velocity, and both observe the same light signal, so this wiggly thing is, imagine that as a beam of light. Both of them see it moving at the same velocity. Of course, our intuition would make us think that the observer who's moving sees it moving more slowly. That would be what you would naively expect. But what happens in reality is that both see it moving at the same velocity. This is due to the fact that time flows differently for different observers. And so the flow of time depends on how you're moving. And so it's better to think about space and time into the new kind of geometry. So that's a new sort of generalized geometry that we use to describe space and time in physics. So this is a yet new type of geometry. So here, remember when we talked about the card game, we redefined the points to be the cards, for example. So here we think of the points as being not a point in space, but a point in space and time, so an event, what sometimes in physics we call an event. So we have to say also at what time it happened. And lines could be the trajectories of particles, so a particle that is at rest is described as a line that is extended in the time direction. So here, for example, in the vertical direction of the screen, we see the time direction, and the horizontal direction, we imagine that to be a space direction. And so we write these diagrams, which we call space-time diagrams. So here we see a vertical line that would be, let's say, a particle at rest, and we see two events that happen for this particle at rest. And we could also have events that happen at different locations at different times, such as these other points. A particle that is moving would be written in this diagram as a line that is not vertical. So this is a particle moving to the right. And in this way, we can have various particles. So the particles that I shown later are moving faster, and the fastest moving object would be a beam of light, which in these diagrams would be moving at 45 degrees because we've chosen the units of length, let's say, to be light years, and the vertical line also in light years. So then we have that light rays would move at 45 degrees. So we'll be drawing some other space-time diagrams later in the talk, and we'll continue to use the same picture. So the conclusion is that out of space and time, we can make a geometry. Now, we'll make now an apparent detour from geometry, and then we'll get back to it. So we'll discuss the force of gravity, as you probably have learned it in high school. So you learned the Newton's law, which says that if you have a heavy object and then a lighter mass, the acceleration of the lighter mass is given in terms of the Newton constant, the mass of the heavy particle, and the inverse of the distance squared. So that's the law you learned in high school. And it has two features. One is that the acceleration of the small particle mass is independent of the mass. And the second is that the force is instantaneous. So if you move let's say if you move the heavy mass, then immediately you see that the direction of the force changes. So at some time the heavy mass is here, the force points this way. If you immediately move it, the force points in another way, and you would immediately notice that. Now, that is not consistent with the principle of relativity, and that presumably should be changed. Now, on the other hand, this first point, point number one, is something that is an interesting feature of gravity that led to what Einstein called his happy thought. So he imagined the following thought experiment. He didn't actually carry out this experiment, he just imagined it. He imagined he's in an elevator, and someone cuts the cables of the elevator. Then the elevator will start falling, and the person inside the elevator will also start falling, but they both fall in exactly the same way with the same acceleration. They will have the same velocity also. And so the person will feel that he or she is floating inside the elevator. And if initially the person was standing on a scale, the scale would show no weight after they start falling. Okay, so that's so in some sense, so what Einstein concluded from this is that gravity is a special force because when you are falling free, gravity disappears. It looks like the force of gravity completely disappears when you are falling freely. Now, Einstein didn't do the elevator because if you actually did it with an elevator, there's a safety mechanism that prevents the elevator from falling. Anyway, so that's what astronauts are falling on the Earth or are in orbit in exactly the same way as the spaceship, and that's why they feel they're floating. Now, that happy idea that Einstein had led him to think about the theory of general relativity, which is Einstein's theory of gravity. It's our modern theory of gravity. And it's based on the idea that space-time is curved, it's not flat. It's the same type of transition we went from Euclidean geometry to describe the surface of the Earth, where we had a curved space. Now we go from the flat space of special relativity to the curved space of general relativity. And when a particle moves in this space, it's moving along the shortest, the trajectory of shortest length, or more precisely, its longest time, and it chooses that trajectory according to the local geometry of the space. And then there is another important element, which is that matter curves the space-time. And so there are some equations, Einstein's equations, which say that the curvature of space-time is equal to the amount of matter that we have. So, and that determines then the shape of space-time. So space-time is a curved geometry, so similar to what we discussed before, the points are events, and in some sense those straight lines are the trajectories of observers that fall freely, and for everyday experience, we are pretty close to flat space. But we can definitely measure the curvature of space, and we can do an experiment very similar to the one by Eratosthenes that used the light from the sun in that case, but in this case we can use the light from very far away galaxies, and then if you have some more nearby galaxies, they act as a lens that curves that light, and we have an effect similar to what Eratosthenes was measuring. Now, there is one very interesting prediction of general relativity, which is related to that point that we saw about Newtonian gravity, saying that we cannot have, so Newtonian gravity, the information travels instantaneously, but in general relativity, it doesn't travel instantaneously, it's transmitted by waves and by gravitational waves, and so the existence of gravitational waves is one of the predictions of general relativity, and it's a prediction that was very directly tested by the new gravitational wave observatories that started working in around 10 years ago, and that has revolutionized this field of gravity and research in gravity. Now, that is perhaps a not very surprising prediction of general relativity, because we saw that it solved the problem of Newtonian gravity. But there were two very surprising predictions of general relativity, which are the existence of black holes and the expanding universe. And this prediction was so surprising that Einstein himself didn't quite believe it. So in fact, Einstein told Lemaitre, who was one of the people who was talking about the expansion of the universe, he told him, your math is great, but your physics is dismal. Okay? And I like this phrase very much because it is what sometimes other physicists tell us, string theorists. Now, we now have great evidence of both things. We have pictures of the gas near the black hole at the center of our galaxy. And we have great evidence of the expanding universe from the cosmic microwave background and many other observations. Now, we'll discuss those topics a bit more later, but we'll now turn to a new topic, which is quantum mechanics. So far we've been discussing, we went from classical physics and discussed special relativity and general relativity and how geometry is so central to general relativity. And now we'll discuss some aspects of quantum mechanics, which is one other important revolution of the 20th century. So quantum mechanics is a new type of description of physical systems that is intrinsically probabilistic, and there are new principles like the uncertainty principle that we cannot determine the position and velocity of a particle, or there are some quantities that we cannot know at the same time. I won't describe all the details of quantum mechanics, but it explains chemistry, matter, atoms, all of those things. Now, it's a weird explanation where atoms are mostly made out of empty space, and usually it requires a lot of work to explain some simple things, like the appearance of most of physical substances are emergent properties. So if you want to explain why the glass is transparent, you need some, and why the table is not transparent, you need to work and explain why that is the case. So many of these properties arise from the collective behavior of many atoms. They are not properties of one atom, but they are properties of many atoms. For example, to us, the mountain appears very solid. To an insect, the surface of the water appears equally solid. In fact, in both cases, they mostly consist of empty space. And if you were a neutrino or a particle of dark matter, you would go through the whole Earth without any interaction, so without noticing anything. You would really see that it's mostly empty space. So we keep introducing concepts. So now one more concept is a type of theory that results from the marriage of quantum mechanics and special relativity. So that's the type of theory you need to use when you have particles that are moving very fast, very close to the speed of light. And that's the type of theory we use to describe elementary particles. So in this type of description, when we have, for example, light, we represent it as a particle called photon, and we describe all interactions in terms of interacting particles. So in the same way that we were using geometry to describe lines and images, we use a similar type of diagrams, space-time diagrams, of particles moving in space-time to describe elementary particles and their interactions. So behind these diagrams, so each of these diagrams corresponds to some possible trajectory of these particles, and there is a mathematical rule that allows us to calculate the probability of this trajectory, and that's the quantum mechanical prediction, is the prediction of those probabilities. And in this way, we can describe particle collisions, such as the ones that are occurring in the Large Hadron Collider that allow us to explore nature at very short distances. So in this way, we can describe all the matter we see. And an important question that remains in this whole series of generalizations is how to put together general relativity with quantum field theory or with quantum mechanics. So how to put together these two important revolutions of the beginning of the 20th century. Now, there are two approaches to this. So there is one approximate approach, which is similar to the one that is used in quantum field theory, and then there is a more precise approach, which would be a full theory of quantum gravity. And each of them has some advantages. So first I will describe the approximate approach. So the approximate approach corresponds to adding a new particle that is related to the force of gravity, which we call the graviton. It mediates the force of gravity. And then we draw the same type of diagrams that we were drawing previously. And this approach works very well when the radius of curvature of your spacetime is much larger than the Planck distance. So Planck distance is some particular combination of fundamental constants, which, if you know scientific notation, that's the number. If you don't, it's just a very, very tiny number. Okay. So just to explain more or less what how tiny this number is. So we have this horizontal line represents an everyday distance. The green line represents the distances the smallest distances we can see today, just the ones we can measure in the LHC, and the Planck distance is just the smallest one over there. But this is not a linear scale, it's a logarithmic scale. So this is this size represents the size of the number of zeros that you have in your measure of distance, or you have in your exponent. The number of powers of 10 that you need to go down. So we need to go down a certain number of powers of 10 to get to the smallest distance, and we need to go down almost an equal number of powers of 10 to get to the Planck scale. So it's a super tiny distance. That's the point we want to convey here in this transparency. Okay, and this is a basic length scale in quantum general relativity. At this length scale, the quantum effects are very important. So if you're doing something at longer distances, they are not so important, and the approximate method works very well. Now, this approximation of thinking of the Planck distance as very tiny is good enough for almost everywhere and for everywhere in the universe and everywhere in daily life. Okay. Now, there are a few places where this approximate approach fails completely, and that happens at the singularity of the beginning of the Big Bang and the singularity in the interior of the black holes. So I haven't defined the word of singularity because singularity means that we don't know what's going on. So if you don't understand the word singularity, that's exactly also what we're feeling. So we don't understand. So it's a place where the approximate methods that work very well in other circumstances do not work. So to understand what happens there, we need a full theory of quantum gravity, the full quantum gravity theory, and that's the main motivation for developing that full theory is to understand the beginning of the Big Bang, or the beginning of the expansion of the universe. Now we'll come to the full theory later, but we'll now want to go back to the approximate approach and describe some interesting successes of the approximate approach. So one of them is that it leads to a big surprise for black holes. So let me describe this big surprise. So it was discovered by Hawking in the 70s. He found that the laws of quantum mechanics in the presence of black holes imply that black holes emit thermal radiation. Now, this radiation is at some temperature, and the temperature increases when you make the black hole smaller. So if you have a big black hole, it will be very cold. If you make it smaller, it will become hotter. And if you make it even smaller, it become even hotter, become white. So this leads to the interesting prediction that you could even have a white black hole. So this effect is so surprising that even the name of black hole was wrongly chosen. Now, for black holes that are astrophysical black holes, so those are the black holes that form naturally during the evolution of stars. These black holes are relatively big, of a few kilometers in size, and they have a very, very tiny temperature. So tiny that there is little hope of measuring this temperature. On the other hand, we could imagine black holes which are very small. So if you had a black hole the size of a bacterium, then that black hole would look white to our eyes. So you look at this black hole and you see a white little dot. So that's, for those black holes, the Hawking radiation is visible. It's a visible effect. It's not visible for very big black holes. Now, you can ask, why does this happen? So we'll discuss now a rather long explanation for why this effect happens, which hopefully will be useful for some other concepts. We'll develop some concepts that will be useful for the rest of the talk. So the first point is that the quantum vacuum in relativistic field theories is a rather complicated thing. And it's complicated because we have fields, and fields are dynamical objects, and we cannot set the field to be zero, because if it was zero at one time and it was zero at a later time, it means that so the shape of the field is a bit like a position of a particle, and it's the motion of the field has to do with its velocity, so we cannot set both to zero at the same time. And so quantum mechanics implies that if one is zero, the other one is not zero, and vice versa. So fields are always non-zero. And in fact, if you measure them at various times, you would get different answers for the values of those fields as you measure them. Now, especially if you look at the little piece of the vacuum, you will see some randomness. You get different answers as you measure. If you look at the whole vacuum, it's a more predictable state. So in some sense, what I'm trying to convey is that the fluctuations are correlated. So if you see that, let's say, the value of the field goes down here, then it will go up in some other location. And so they are correlated. More precisely, in quantum mechanics, we call this entanglement. So entanglement is a type of correlation that's a bit stronger than classical correlations. I won't discuss it in great detail. For the purposes of this talk, let's say they are correlated in a way that the average value of the field has to be 0. So if it's up here, it's down in the other region. So let's describe this type of correlations that we have in the vacuum with an analogy. So let's say that someone tells you the portion of a sentence. So for example, the sentence, Mary looked for the ingredients, okay? Now, what does this sentence mean? Well, it could end in many different ways. And now, on the other hand, if we see the full sentence, so Mary looked for the ingredients for the new superconducting material she's making, then you have the full sentence, okay? And it has a unique meaning. So that's similar to having the full vacuum, okay? So if we have only a portion of a sentence, we lack some information, and we could, in principle, quantify the information that we lack by listing the various ways in which we can complete the sentence. And we can call this the entropy of associated to the sentence. So this is entropy, some amount of information. So it's an idea in information theory of how much information we're lacking to complete the sentence. By the way, ChatGPT computes this type of entropies. Now, the full vacuum is a well-formed sentence, and a small region is a bit like a portion of a sentence. Okay, so now, after this long discussion about the vacuum in quantum field theory, we'll go now back to black holes. So now here we are trying to represent the space-time diagram of a black hole. So let's describe the space-time diagram a little bit. A black hole is a four-dimensional object. We're thinking about the spherically symmetric black hole. So we're not going to draw the directions of the sphere. So each point on this diagram is a whole sphere. So we're going to only represent the radial direction of how far you are from the center, let's say, along the radial direction, and also the time direction. So the vertical direction in this diagram is roughly the time direction, and the horizontal direction is the radial direction. Okay? Now we've also kind of deformed and projected the geometry of that black hole to a plane, to a two-dimensional plane, and we deformed that geometry, but we kept the angles. In particular, light rays are still propagating at 45 degrees in these diagrams. So after we did all that, this is the geometry of the black hole. The vertical line to the left, that could be viewed as the center of the star that formed the black hole. We haven't drawn here the star. The red line represents a singularity. That's a region where the space-time curvature becomes very large, and if you happen to get close to this region, you die. Okay? So that's somehow where space-time ends. So the interior of the black hole is the region that is between the black line and the red line. I'll describe what the black line is in a second, but that region looks like a collapsing universe, and you collapse into singularity. Now, as we said, light rays are lines that move at 45 degrees, so lines that are moving at 45 degrees to the right represent outgoing light rays, so light rays that are moving out of the black hole if they are below that black line. Okay? The black line is a special light ray, which we call the horizon of a black hole, and if you're moving along that black line, if you have that light ray, that the size of that black ray, that collection of black rays, the size of the two sphere is not increasing. So, and then if you are a light ray that is on top of this black line, then you will hit the red line and you fall into the singularity. So you cannot avoid, once you are above the black line, you will be, all you can do is fall into the singularity. You cannot avoid falling into the singularity because in order to avoid getting into a singularity, you have to travel faster than light, but you cannot do that. Okay, so that's the geometry of the black hole. Now, someone who is outside the black hole would be in the region that is on the top right of the diagram, and that person can only receive signals from points that are below the black line, okay? So they can receive signals which would be lines that move at 45 degrees outwards, okay? Because any point that, that is above the black line, if it intends to send the signal to the person outside, will send the signal to the right, but that signal will get to the singularity and will not come out, okay? So a person who's outside will see only a portion of the space. And now, this is a space-time that contains a physical vacuum, right? So it contains all the fields of the standard model, etc. So we have the vacuum state, which was a full state, but the person outside sees only a portion of this state. Sees only a portion of the vacuum. And because it sees only a portion of the vacuum, it lacks, it's lacking some information. It will see it not as a complete state, as a well-defined state, as a single state, but it will see it as a series of possibilities, let's say. And so it will have some entropy. So that full vacuum is a bit like a sentence, and we see only the portion of the sentence that is outside the horizon, okay? And that is basically the origin of the randomness or the temperature that is associated to the black hole, and that's the origin of Hawking radiation. I didn't explain exactly where the formula for the temperature comes from, but going a little bit more, we would be able to explain it, but we won't see it today. So now for a black hole, you can use the laws of thermodynamics to calculate the entropy, yeah, so once you know the temperature and the energy, you can use that laws to calculate the entropy, and the entropy turns out to be equal to the area in Planck units. So remember that Planck length was super tiny, so this entropy is super big, and so it's bigger than the entropy of any everyday object with the same size. Okay, and not only that, but the second law of thermodynamics, so the idea that the entropy should increase, can be derived from Einstein's equations, and it says that the area of horizons always increases. So for example, if you have two black holes that collide, the area of the final black hole is bigger than the area of the initial black holes. Okay, so now what this implies is that black holes emit radiation and they lose mass. We call this the black hole evaporation. It's a bit like you have a piece of water that is emitting, well, vapor coming out of a piece of water, and it becomes smaller, and something similar happens to the black hole. Now this process, as we said, is irrelevant for astrophysical black holes, but let's say, suppose you had a black hole that had a mass of 1 kilogram. I mean, we don't know that whether these black holes exist or not in the universe. Probably they don't exist, but if someone were to give you a black hole of a mass of 1 kilogram, would you accept it? Now, you might be worried you would fall into this black hole, but this black hole of mass 1 kilogram doesn't exert a very big gravitational force. So it's a black hole you could carry in your pocket, basically, you might think. But there's a small problem with this, which is that it will emit a lot of Hawking radiation, and the temperature will be so big that it will emit all its mass in a tiny fraction of a second. So it will be a big explosion, bigger than the explosion of an atomic bomb. So you should not accept it. Now, fortunately, there are no such black holes around. Now, so far, we described some results for black holes using the approximate method. Okay? Now, there are some questions we cannot answer using the approximate method, such as precisely what comes out of the black hole. So is the information of what formed the black hole, is it still contained in the radiation that comes out in some scrambled way or not? Now, why would we think that it should be contained? Well, we would think it should be contained because the laws of quantum mechanics preserve information. So if you have some initial state and you had two different initial states, they will lead to two different final states. The differences might be super tiny, but in principle, it's a question of principle of what are the laws of nature. Do they preserve or do not preserve information from the point of view of an observer who sits outside of a black hole? I mean, to answer this question, we need the full theory. Now, we have a theory under construction, and we call this theory string theory for historical reasons, but it is a theory of quantum gravity that tries to describe quantum spacetime. And in fact, we just had here the Eurostrings conference for the last 4 days, where the latest ideas in string theory were discussed. Now, string theory is a theory under construction. Its form is not totally fixed, and it's a bit like this building. We think it's there, and we're trying to see it better and better, and this conference was part of trying to understand it better. But now the task is to explain it without mathematics. So without mathematics, it's less clear that it's there, but we'll try our best. So we're learning, using this theory, we're learning some interesting aspects of quantum black holes, and we'll focus on just only one aspect of this. There were many, many different aspects that were discussed during this conference, and we'll focus now the rest of the discussion in only one of these aspects. And this aspect will be the idea that space-time itself could be an emergent concept. So in the same way that this insect sees the surface of water as an emergent concept that comes out of the interactions, if you wish, of the molecules of water, it's not a property of a single molecule of water, it's a property of many water molecules. They make up the geometry and surface of where the insect stands. The question is whether there are some other similar atoms, let's say, or fundamental units that make up space-time. So what are these space-time atoms? So the idea is that we could have some space-time atoms. There would be some qubits, some basic quantum units. And the idea is that these quantum units, we should think of them as living on. So this description, we understand it only for some spacetimes, which are spacetimes which are curved, have constant negative curvature. They're similar to hyperbolic space. And in these cases, we can think of the whole geometry and gravity in these spacetimes in terms of qubits or particles that live on the boundary of this spacetime. So the boundary is some region far away, so you can think of this as hyperbolic space. So this picture here represents a hyperbolic space projected onto the flat surface. So each of these fish has the same proper size, and there is an infinite number of fish as you go out in the radial direction. That means that what we're calling the boundary is really infinitely far away. And in the same way that when you project the surface of the Earth onto a flat surface, some regions get deformed. Here, the region that is far away got deformed, got shrunk to a finite size region. And so we should think of this as of the particles that live on this surface that is far away. Now let's say this in a different way. So the idea is that if we have a particle moving in the interior of this spacetime, the yellow particle, that can be understood as equivalently as some other collection of particles that move purely on the boundary, so move along, in this case, a one-dimensional boundary. Now here we represented the motion of these particles as somewhat random and moving in a complicated way. What that tries to represent is first that these are quantum particles, second, that they are interacting strongly with each other. They are strong interacting particles. So that's the idea. And if we had a black hole inside this geometry, then that black hole would again be described by a collection of particles that moves on this boundary. And the entropy and temperature of these black holes would be related to the temperature and entropy of these particles that move on the boundary. And in some concrete cases of examples of this relationship, we can calculate that entropy and find agreement. Now here I got tired drawing these little dots that you see there. It really should be viewed as a fluid with many, many, many particles. Okay, so the theory on the boundary obeys the rules of quantum mechanics. And so then you would conclude that the black hole in the interior also obeys the rules of quantum mechanics. So black holes should be consistent with quantum mechanics and information should be preserved. Okay? This is what you conclude from this. Of course, subject to the fine print, and the fine print says if you accept this holographic conjecture, which is a conjecture that we're trying to understand better and better, and it's getting understood better and better, but it's still a conjecture. So now let's emphasize one aspect of this holography, which is this idea of an emergent geometry. So let's consider, for example, a case where the space is two-dimensional and the boundary has a one dimension of space. So the idea is that the qubits live on that line, and the gravitational space-time or the geometry has one more dimension. So this is this idea of an emergent geometry, and we'll make an analogy. Now, for this analogy, imagine a phrase, some famous phrase of the English language that says that if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. This is a famous phrase by an American writer. Now, when you hear this phrase, you can your mind automatically separated all the sounds in different words, and then your mind also separated the words into different concepts: the subject of the phrase, the predicate, the verb, etc., the various clauses of the phrase. So it did the whole analysis of this phrase, finding a deeper and deeper meaning. So in order to find the deep meaning of the phrase, you need to do this analysis. And the phrase contains words that are correlated with each other, such as man, his, and he are all correlated. Or there is a deeper correlation, perhaps, between keeping pace and drummer. So there are all these correlations between the words, and it is all these correlations that give meaning to the phrase. Now, what does this have to do with the geometry? So the idea is that the state of the quantum system is a state where all the qubits are correlated with each other, and they have some meaning that the geometry is analyzing. So the geometry is a bit like an analysis of that phrase, and features of the geometry are telling us about the correlations that exist among those qubits that live at the boundary. Okay. And the fact that these geometries are self-similar is related to the fact that those correlations also have a self-similar pattern. And even particles that propagate on this geometry can be viewed as arising from special correlations that exist between different parts of the quantum system. So you could maybe poetically say that someone who lives inside this space-time is a bit like a character in a novel that is written on the boundary. Now, perhaps more accurate way to describe this is that because this is a quantum thing, the boundary is a superposition of many possible sentences, and the bulk represents a statistical analysis of the correlations present in those sentences. So it's a bit like a language model. Now, what is a black hole in this space-time? So let's go back to the sentence. This is exactly the same sentence we had before. And now let's just change some words. So here we changed randomly some words. And so now the sentence, we lost some correlations. So we lost some correlations that existed between the words, and the sentence doesn't make as much sense as it made before. So you can analyze it, and it has a meaning up to a certain level, but it lost its deeper meaning. Now, there is something you can say, it's a horizon of meaning. So you can analyze it up to a point, and then it ceases to make sense at some point. Now, we could make more changes, so make more random changes, and then the sentence makes less sense, and you can only analyze it to a more shallow level, and so the horizon of meaning has grown. Okay, and so If you change a sentence randomly, it will make less sense than before, and so that's related to the second law, that the random changes will mess up a sentence, and the sentence will make less sense afterwards. The horizon grows, our ignorance will grow. Now, on the other hand, imagine we change it completely and we have this random mess. But imagine this random mess came from some encryption process, like the ones we use in the computers to send our credit card information. So when you have such a situation, then someone who knows the key, the process, what's important is that the encryption process is reversible, so we can reverse the process and recover the original sentence. Okay? Now, the laws of physics on the boundary change the state of the boundary, and sometimes when we start with some state, it might complicate it and create, let's say, a black hole. But because these laws are reversible, we in principle could run time in the reverse direction and recover the information and recover undo the original black hole formation and recover the original information. Okay. So the lesson is that we get from here is that space-time emerges from these correlations, or more precisely quantum entanglement, and that's how geometry emerges, in a way that is somewhat similar to how correlations and meaning emerges from sentences. Now, the bottom picture is a picture from a paper that talks about quantum entanglement in physical systems. The only purpose in me showing this picture is just to show you that it looks similar to the top picture, okay? And it also looks similar to the pictures of the geometry of hyperbolic space. So the bottom picture is the actual picture people use to, there are some mathematical formulas behind this picture that enable us to encode the behavior of quantum systems, of entanglement in quantum systems. So we could go back to Galileo's phrase we started from the beginning and say that we have, the book of nature is the state at the boundary that is written in some language from which geometry emerges. So that's the end of the analogy for now. So we'll now discuss some extreme case of the relationship between entanglement and geometry. And so there is a funny feature with the simplest black hole solution. So this is the black hole solution of that Schwarzschild found. So that's the simplest solution of Einstein's equation with spherical symmetry that Schwarzschild found 1 year after Einstein wrote his equations. And the funny feature is that it describes not one black hole, but actually two black holes. Okay? So we can think of that solution, or a solution that is pretty close to that solution, as two black holes that are very, very far away, but they share a common interior. Okay? So, in fact, the spatial geometry of the solution looks a bit like a wormhole. So the two regions that are far away are connected through the interior. Now, the interior is time-dependent. It stretches and collapses, so a traveler cannot use this to travel from one side to the other. You cannot use it to send any information between the two exteriors of the black hole. So at some instant in time, the spatial geometry looks similar to the diagram there in the middle, where you have a three-dimensional space. Then you reach the black hole horizon of one black hole, and then you connect to the black hole horizon. You connect to the exterior of the other black hole, and then you go out the other black hole. That's how the spatial geometry looks at some instant in time. At a later instant in time, the two separate, it stretches and shrinks. Okay? And eventually it shrinks completely, and so when it shrinks to zero size, that's the singularity. So that's the geometry of the black hole. Now, we said that if we look at the black hole from the outside, we can think of it as, so in holography it was some collection of particles, but in general we expect it to be some quantum system that will have certain number of states and so on. And the idea is that this geometry should be interpreted as two entangled black holes. So those two quantum systems are entangled with each other. And with entanglement, you cannot send signals fast. You cannot send any kind of signal. And indeed, that agrees with the feature of the geometry, which is that you cannot send signals through this Einstein-Rosen bridge, or that wormhole that we discussed. So let me make some analogy for this entanglement or this wormhole. Imagine you have now the phrase we had before, so that's in the top of the picture here, and we have the same phrase, let's say, in another language, let's say in Spanish, got it? And now when you, the words are different, but they have a common meaning. So we start analyzing these phrases, we reach to a point where they have a common meaning. So a common meaning would be the line in the middle that represents the center of the wormhole. Now, these wormholes that form in this case are not traversable, but you can, there are some variants where you bring the black holes a little closer together, and through in some special cases with some special interactions, the wormhole can actually become traversable, and the whole configuration ceases to be a black hole and becomes a traversable wormhole. And so I won't describe this in detail, but this is related to traversable wormholes. But unfortunately, these are not wormholes that allow you to travel faster than the speed of light, so they are not the science fiction wormholes that appear in science fiction books. These are wormholes where it would take you longer to go through the wormhole than outside the wormhole. Now, in quantum mechanics, this idea that from the quantum system point of view, this idea that an equivalent phenomenon is called quantum teleportation. And when space-time is emergent, as it happens in these cases, then you can view this teleportation as just transmission of signals through a wormhole. Now, we'll now do a small analogy for quantum teleportation through a wormhole. So teleportation has three elements. One is entanglement. The other one is some communication, and the third thing is a wormhole. So imagine that we have two people, Bob and Alice, and they've been married for many years. They share many common memories. Okay, that's analogous to entanglement. These shared experiences. Okay. Now, might be some communication. The communication might be a look. Let's say Alice looks at Bob, okay? And then the transmission of the wormhole is that Bob knows what to do, okay? So, I mean, the idea is that, the analogy is that there is some, there's Bob's mind and Alice's mind. There is some emergent universe of ideas in each of these minds, and the look, that communication, allowed an idea to go from Alice's mind to Bob's mind. Okay, so now I've discussed these wormholes, but similar wormholes are useful for understanding how information is encoded in Hawking radiation, and how the black hole, how it can come out of the black hole interior. And there was very interesting developments a few years ago by these authors, Pennington and Mary Engelhardt, Malcolm Maxfield, and Sarchenko and Stanford, that have used these wormholes and have understood this problem much better. Now, in conclusions, I would like to say that so quantum systems give rise to geometries through correlations, and that our spacetime perhaps could be emergent. Now, our spacetime is not negatively curved, as we discussed here. It's mostly positively curved and expanding universe. And part of the recent research activity is trying to understand whether these relationships can be also generalized to our own spacetime. Now, there is some interesting consequence of this idea, which is that we could make tiny universes in our laboratory. So what would that mean? So the idea is that we could make, with a sufficiently sophisticated quantum computer, a quantum system that is complicated and strongly interacting enough that it makes a tiny, universe that is governed by Einstein's equations. So by universe, we only mean something that is governed by Einstein's equations. We don't mean such universe as big as, so the word universe usually makes you think of something very big, right? But we physicists think about alternative universes, which could be very small, and we call it universe as long as it's governed by Einstein's equations. That contains geometry, contains the same elements that Einstein theory has. And you can calculate how many you would need. So you would need about 10,000 qubits to make the tiniest little universe that you can barely say it's governed by Einstein's equations. The more qubits you have, the better it will be described by Einstein's equations. Now, just in contrast, for our big universe, we would need roughly 110 to the 120 qubits. And that's even to create a universe as big as ours, but with negative cosmological constants. So, okay. So it will be a very tiny little universe. But, well, when will this be done? So if you read the newspapers, it will be in 2 years, because doing this is as difficult as breaking the RSA codes. I'm joking when I said 2 years, but but, well, maybe it will be done in 30 years, perhaps, I don't know. But that will be an interesting application of quantum computers. Now, in the future, we will hopefully understand the singularity inside black holes. That's something that is not currently understood. And this will hopefully also lead us to understand the beginning of our universe, which again is something that is not been understood and is the main objective in our developing of, well, in the idea of developing a theory of quantum gravity. Okay, thank you.
Thank you very much, Juan, for the very interesting talk. So we can have questions from the audience. Who wants to go first? Yes?
It was a very, very nice presentation. Thank you very much. It was delighting. I would like to ask you the following. For example, Grigori Volovic, he says you have correlations that creates a P-wave superconductor when you are at the node that is topologically stable. At low energy, you see Dirac fermions. So you have an emerging geometry through correlations. Do you say the same thing about the bulkheads, this holography principle? Does it mean that there is a many-body system that creates an effective medium that represents the geometry, what you call the geometry that is equivalent of having modified geometries?
Yeah, unfortunately, there is some echo here, and I couldn't hear your question very well. Maybe I should. Is there a portable mic? Maybe. I couldn't hear the question very well. Maybe if I stand further here, maybe if I come closer, I could hear the question better. But I think you were asking about how geometry emerges from quantum system and a quantum many-body system.
We have a many-body system that is correlated and can lead to a P-wave superconductor. In the low wave superconductor, at low energy, we have Dirac fermions. That is the
okay, yeah. So let yeah. Yes. Yes. Let me. Yeah. Okay. So so the question was about the condensed matter system, which is a superconductor that has some correlations between the particles. Now, the systems we are talking about have stronger correlations, are more complicated correlations. So superconductor has correlations that are too simple to give rise to a geometry. Yes. Okay. Okay. Good. Yeah. So high TC, for example, superconducting materials are more strongly correlated than the old PCS superconducting materials. I think you are referring to those. And as far as we understand, those materials don't have a geometry that is governed by Einstein's equations, though people sometimes use Einstein's equations and so on to perhaps study some aspects of strongly correlated systems that are closely related to those superconducting materials. No, I don't know about that. Well, yeah, I think we're turning into some details. We can discuss them later if you want. Yeah, I'm happy to discuss later. Yep.
So you said that if we are to replicate our universe in a quantum computer, that would need around like 10 to the 120 qubits if the cosmological constant is negative. Would that change if we have, like, let's say, an expanding universe with positive cosmological constant, and if yes, why?
Well, that counting is expected to be the same. Probably, if there was a holography for our de Sitter universe, and there are some ideas of how this might work, you would also need a similar number. Now, of course, this is not the number that we could actually manipulate and do it. I mean, this would be the number that someone else could use to build our universe. I'm not sure if this is clear. Where does this number come from? Let me just mention where this number comes from. In the Sitter space, or in an expanding universe with accelerated expansion, as we expect as we have now and we expect to continue to have in the future, we'll only be able to see only a portion of the universe. There is a horizon similar to a black hole horizon, and we can calculate the area of this horizon. And the area of this horizon in Planck units is that number of 10 to the 120. It's the same formula for the entropy that applies for black hole entropy.
Anybody else?
I just wondered, if we had a non-traversable wormhole and you tried to go through it, what would actually happen to you?
If you have a traversable wormhole or a non-traversable wormhole? Let's answer for both.
Okay.
So
okay.
the non-traversable wormhole, that would be like these two black holes. So you would go in and you die in the singularity. So it would be similar to falling into a black hole, so not very pleasant. In the traversable wormhole, so it depends on the particular setup, but you would feel you are falling in, and then you come out, and you come out happily on the other side. If the wormhole is big enough, so that the tidal forces. So usually when you're in a curved space-time, you feel what we call tidal forces, which are gravitational forces that pull your head and your feet in different directions, right? Similar to the tides in the Earth that deform the Earth. We are quite sensitive to these forces, so we need the curvature of this wormhole to be sufficiently small. How small? The radius of curvature. The radius of curvature has to be comparable to the size of the Earth. That's the type of tidal forces we can tolerate.
I wanted to ask you if you believe in de Sitter CFT correspondence or not, in your personal opinion, considering. Yeah.
Well, some days yes and some days no. I don't know.
Okay. Thank you.
But yeah, in the sitter there are two ideas that people have explored for holography. One is this the sitter CFT, which is the idea that we think about the future of the sitter, the future of this cosmology, and we think about all the various observers that could live there, and they don't communicate with each other. But in the same way that in negative curvature there is a boundary that was these circles that we were drawing, or that those lines we were drawing in hyperbolic space as the boundary of hyperbolic space, there's a similar diagram for our expanding universe. And so you could imagine a theory that lives on that spatial slice. So it would be a three-dimensional surface with no time. And so there would be a statistical system there, and time would be an emergent property. So we will just only talk about the state of the universe at the end of the universe, and the whole history of what happened before is contained in the correlations of that universe. Now, well, one fun thing is that if we look at the early universe, there was a period of so-called inflation where the universe was expanding very rapidly, and so it expanded very rapidly, and it contained some perturbations and so on, and then it stopped expanding. And so when we look at the universe now, at the very early universe, we are looking at this region that from the very early universe was the very far future, right? So we are some observer who can look at all these regions, and all the things that happened during that period are contained in correlations of the fluctuations that we currently see in the cosmic microwave background. And so there is a sense in which we are reconstructing the time direction or we could in principle reconstruct this time direction of what was happening by looking at the cosmic microwave background, by looking at the fluctuations. Now, we don't have sufficient statistics to reconstruct too much, but it's something in principle could be done. But so that's one approach to holography, and then there is another approach which is centered on what an observer in the sitter would, in that expanding universe would feel. So we are these observers, and we imagine existing forever, and we have this horizon, and we describe just whatever is inside our horizon. And so there will be some theory that perhaps lives on that surface, or perhaps lives in some abstract space. But that will be describing not all of the expanding universe, but just the part that we can observe. So those are two main ideas that people have explored.
Hello. Your example with Bob and Alice and their universes sort of reminded me of Roger Penrose's sort of ideas of using quantum mechanics to understand the notion of consciousness. What's your thoughts on that? Can we use quantum mechanics to understand consciousness?
Well, I don't know how to understand consciousness, but I think these ideas of Penrose are non-mainstream, so they are out of the mainstream for the reason that we think that quantum correlations and entanglement would be lost very quickly in the brain, which operates at some finite temperature and is pretty messy. So people think that it's a phenomenon that probably can be understood using classical physics. That's the mainstream opinion that I hear from specialists.
Recreating the little quantum with the 10,000 quantum bits, would it be the first step to do quantum keys distribution?
Yeah, you would need to have a quantum computer that allows you to manipulate qubits and with. So these are 10,000 qubits are with error correction, and so these are 10,000 logical qubits. So we are very far from this.
So if one can engineer the emergent spacetime with qubits, then what would be required in order to then create a black hole in the bulk in some sense?
Yeah, so in this example, so we could have a little universe with a black hole in it, with a big black hole in it. And then you would have to have this system at finite temperature. So it would be somewhat naturally constructed with a black hole. It would be easier to make it with a black hole than without a black hole. I should mention that there are some simpler things you can do than a universe governed by Einstein's equations. So some systems of qubits that display some aspects of this story, maybe not all the aspects, and people are building them and are exploring some of these issues. So.
Greetings. It's actually an honor to pick me, Doctor. Well, as you previously said, there are not any active black holes around us. But I will actually want to point out that there is an active black hole inside the center of our galaxy called Sagittarius A. So my question is this. At one specific distance do these heavy objects, just like black holes, start to be considered as a threat to the humanity and to the solar system in general?
Okay, so the question is whether black holes are dangerous, right? Is that the question, basically? Yeah. So the black holes that are known to exist, they form from the collapse of stars, and they are far away. They're about. They say that there is a black hole every 100 stars or something like that. That's roughly, I think, what the astronomers tell me. And so the nearest star is about 4 light years away. So the nearest black hole, well, it's it's a little bit further. So so they are not a direct threat for us or for humanity or anything like this. Yeah, maybe that's the short answer.
Yes, but at the same time, even though it's not located close to us, we wouldn't say that this far too far away from us either, correct? I mean that even though we have a great distance from the center of our galaxy, there are many other black holes that they are even more far away from us, correct?
Yeah, I mean, there are other black holes, but they are pretty far away, right? They are further than the nearest star. Well, the nearest star is the sun, but the next nearest star.
Thank you very much, sir.
Yeah, sure. Now, just to emphasize this point, if we were to replace the sun by a black hole, of course we will lose the light of the sun, but the Earth would continue to go around and we would not fall into the black hole for a very, very, very long time. Yeah. So similarly, if we have other black holes over there, it's like they're similar to when the star was there, so it's not bothering us at all. Yeah.
Thanks for the nice talk, Juan. Maybe I would like to invite you to speculate on the bullet you have on the final slide about understanding the singularity inside black holes. How did the ideas you presented, perhaps, yes, the thinking about the space-time as emergent and, understanding quantum correlations and so on, the boundary, how would they help us, understand singularities? And you're welcome, I invite you to speculate.
Well, to Speculate. Well, that's kind of dangerous. Okay. One of the things that has been learned from wormholes and these latest developments of wormholes is that the interpretation of wormholes might have something to do with the laws of nature, of things we don't know about the laws of nature, some details in the laws of nature that the low energy observer like us does not know. And that somehow these wormholes are related to correlations that we have in these laws of nature and some randomness in the choice of the precise microscopic laws. And that seems to be something important for constructing the black hole interior. So that might be an important thing. Now, how that applies to the beginning of the Big Bang, or I don't know. It might be that the laws of nature are not known, and as the universe expands, they get more and more fixed, and that may make the universe expand itself, and we reconstruct the history in some way from the correlations we have today. These are all vague things. Well, thank you very much, and see you. Yep.
Thank you very much for
I hope to
coming.
come back soon.